Well, it's a pleasure to be presenting today in the Faraday Theatre of the Royal Institution. It's always a lovely pleasure. Just to start with, I thought I might get you guys to all stand up because I have some questions for you. So can everyone please, I know this is quite difficult for some of you with leg room, but can you all stand up? Thank you. Can you sit down if you've... Okay, remain standing if you've heard of a particle accelerator before. Remain standing if you've heard of a particle accelerator before. Good, okay. Remain standing if you've ever heard of a particle accelerator being used for something other than particle physics. So if you think that particle accelerators are just particle physics, can you sit down for me? Okay? Good. Final question. Remain standing if you think that you can explain, even just vaguely or briefly, how a particle accelerator works. Can you remain standing if you think, I'm not going to make you, promise. Oh, a couple. Okay, thank you. You can all sit down again, thank you. So let's start then, because a lot of you weren't able to say what it was or what they're used for. With this question, what is a particle accelerator? Well, most of you have heard of them, and probably for most of you, the one that springs to mind is this image here. Can anyone put their hand up and tell me what the name of this machine is, if you recognise it? Just shout it out up here.
Large Hadron Collider.
Thank you very much. This is the Large Hadron Collider. It's the world's biggest particle accelerator. It's 27 kilometres in circumference. It's buried about 100 metres underground near the border between France and Switzerland, near Geneva. And we'll hear a little bit more about that. But that's only one particle accelerator. There are actually over 26,000 of them in the world. Hopefully later on we'll find out a little bit more of where they're used. But to start with, let's quickly go through. I won't make those people who are left standing do this for me. I'll tell you very briefly how they work. So we need a few ingredients. And the first thing we need is some particles. And by that I mean subatomic particles, or even atoms themselves perhaps. So here's a little quiz for you. 4 different types of particles: electrons, neutrons, protons, and gold atoms. Can you put your hand up if you think that you know, or think you can tell me which one of those you can't put in a particle accelerator? Can anyone suggest which one you think you can't put in an accelerator? In the centre here? Yep. Can you say it a bit louder? A neutron. Yep. Do you know why? Because it isn't charged. Thank you very much. Okay, so you can't put a neutron in a particle accelerator because it doesn't have an electric charge. Now, there's another one there that jumps out at me that might not have an electric charge. Can someone tell me which one it is? Yep.
The gold atom.
The gold atom, yes. Can anyone suggest a way to get that gold atom into a particle accelerator? Up the back there? Yep. You can ionize it. Thank you. Okay. So to ionize a gold atom, you can rip the electrons off or add more electrons on, or whichever way around you want to do it, give it an electric charge, and then we can put it in a particle accelerator. So that's the kind of particles we need. Now, the next thing we want to do with those particles is to give them some energy. That's the basics of how an accelerator works. You just take these particles, you give them some energy, and you do something with it. So I've got a machine here called a Van de Graaff generator, which does that on a slightly bigger scale. And building up charge, actually building up voltage, is the key to getting particles, to giving particles energy in a particle accelerator. So if I just switch this one on then. Now, some of the first particle accelerators were actually genuinely using this mechanism of having a belt and some rollers and building up lots of voltage. They were called Van de Graaff accelerators. They still exist. I've worked on one, actually. So this isn't actually that far-fetched. But if you pretend that these are some particles which are charged, so if they're the same charge, they get repelled, and there's a force there, they're pushed away, and they gain some energy, which in that case just push them up in the air. But in the case of an accelerator, we'll get our particles up, going faster and faster and faster towards the speed of light. And to make that a little bit more realistic, I have a demonstration here, which is the simplest particle accelerator I could make, which is in a giant salad bowl. Can I have the visualizer on? Someone up there? Let me just put that under here. There we are. So you can see in that bowl that there are some metal strips, and they cross over in the centre. And the 4 in the centre that cross over are going to be connected to the high voltage part of the Van de Graaff generator. Now, the other 4 strips, those ones like that one, are connected to ground or 0 volts. So I'm just going to connect that up. Okay, so in this case, my ball is actually going to be the particle. It's covered in a conducting paint, so again, it will be charged in the accelerator. And, well, I'll pop it in there and see what happens. So if I just switch this on, hopefully we'll be able to see up on the screen there. There we go. Okay, so what's happening here is that when it goes over the charge strip, it picks up the same charge, and it gets repelled, just like the metal cups were repelled, and it gets pushed along. Then it hits the grounded strip, and it dumps all of that charge, but it keeps its momentum, it keeps rolling around. So then it's able to approach the next charge strip without getting decelerated or slowed down. So every time it goes over one of those 4 that crosses in the middle, it gets a kick, or it gets accelerated, and it gains energy again and again, and at the moment, it's actually circulating in the bowl just outside of your field of view there. And it's limited in how far it can go up this bowl by friction and by gravity in this case. Slow it down again. Get it back in view a little bit. So this is a pretty simple particle accelerator, and I think you'll recognize that it's not really how a proper one works. There's a few reasons it's not how a proper one works. The first one is that in this demonstration, the ball has to change charge. And fundamental particles don't change charge. So while in this case my voltage is constant and my particle changes charge, in a real accelerator, we have a constant charge particle, and that means that we have to change the voltage really, really quickly in time with the particles coming around to get them to accelerate. So I'm going to switch that one off. Ground everything. Right, so that's approximately how we're going to give some particles some energy. The next ingredient is how to control them, and for that we use magnets. Hopefully, some of you will know that if you put a current or a beam of charged particles through a magnet, it will actually bend around a corner. So that's how we achieve control. And then there's no point getting these particles up to a huge energy if you're not going to do something with them. So I'll call that collision. And there's no point doing all that great science unless you can see what you're doing. So the final ingredient that I put in the list of things we need for an accelerator is a detector, which in this case was our eye, but in other cases they can get a little bit more complicated. And this is an example of an image from one of the Large Hadron Collider detectors of 2 beams of protons smashing into each other and creating loads and loads of different particles, which you can then see in the detector. That's actually a simulated one, not a real one, but they'll look pretty much identical. But this talk isn't about accelerators. We now know how they work. The talk is about 5 things you should never do with a particle accelerator. So I'm sure when you heard the title of that, you thought, oh, you probably shouldn't do this. So can someone give me an example of something they think you probably shouldn't do with a particle accelerator? What do you think? There's lots of things. They are mostly silly, so please do say them. Anyone? Up there? Put a live animal. You're onto something there, because you know what? That's number 1. I did not plant that, I promise. Right, so the first one, do not try to accelerate a pet. I don't know why as humans we automatically think, I've got this crazy machine, I'm going to put a bunny in it. Anyway, so can anyone think, mostly through this talk we're going to have some crazy ideas, but I want you to try and use your brain, use what you know of physics to think, why couldn't you do that? Anyone? Why couldn't you put your pet in a particle accelerator? Up here? Yep. It's not magnetic, and it's also not charged. Right? It doesn't have an electric charge. Okay, so we could strap 2 of these to the bunny and charge him up, and then he'd be charged. But he's slightly too big. And the other thing that might happen, is he's going to be affected by the vacuum in the pipe of the machine. At least I suspect he would. So unfortunately, well, we had this little marshmallow man who was kind of already carked it over here, but I'm going to demonstrate to you what might happen. Can we get the visualizer back up, please? What might happen? So this is what he looked like, a marshmallow man, when we made him before. But what I'm going to do is suck out all of the air out of this container and see what happens to Marshmallow Man, or indeed what might happen to our pet bunny rabbit in a particle accelerator. Oops. So you might know that as you suck out all the air, oh my gosh, it's huge! That's amazing! Sorry, we haven't tested this. I didn't realise it was going to be this good. Oh, okay, and he's gone past. Okay, so what was happening there is, I'm just going to switch it off while he looks a bit sad. What happened there was, as you suck the air out, the volume of the marshmallow grows. And unfortunately, that's probably what would happen to your little bunny rabbit, but in a slightly more horrific fashion. Now, in this case, a marshmallow is stretchy, so he grew to a pretty good size there, actually. And then once it went past the point of the marshmallow being elastic, that's when he kind of died and shriveled back down again. Is it possible to slowly let the air back in and just...
To what, sorry?
To let the air back in?
Yeah.
Yeah? Thank you. Can you give Andy a big round of applause for helping me with that demo? Thank you. Okay, so that's one reason why you probably shouldn't accelerate your pet. So my number two thing you shouldn't do with a particle accelerator is you probably shouldn't put your head in the beam of a particle accelerator. And on this one, I want to have a little bit of a vote with you guys. So what might kill you first? Would your head freeze because of the cryogenics? So it's at minus 271 degrees in some accelerators, not all of them, but take the Large Hadron Collider, for example. There, the magnets are pretty cold. Or would the heat from the beam make your head explode? Or would your head explode from the ultra-high vacuum? Or would you die from the radiation dose? So I'm going to say 1, 2, 3, 4, and I want a show of hands for which one you think would get you first. So 1, who goes for 1? Who goes for your head freezing from cryogenics? Oh, only a couple of people. Who goes for number 2? Who thinks the heat from the beam? Oh, lots of people. A few people at the top think heat from the beam. Okay. Who thinks the head would explode in the ultra-high vacuum? It's convincing, isn't it? Yeah, there's quite a few people who like that one. Okay, and who thinks you would die from the radiation dose? Who thinks you would die from the radiation dose? Interesting, okay. So what is the answer? Well, I had a bit of a think about it. And the answer is, it depends which accelerator we're talking about. But let's consider the Large Hadron Collider. First of all, let's think about the cryogenics, about that really cold temperature. Well, it's minus 271 degrees. That's very cold. It would definitely freeze your head if you were able to get your head inside the machine. This is a picture of one of the 15-metre long dipole magnets, one of the bending magnets in the machine, and they are cooled down to this temperature. But it's extremely difficult to get your head in there. So if you had any sense about you at all, you wouldn't stick your head in the dipole, you'd stick it in somewhere easier in a bit that wasn't cooled down to minus 271. So the likelihood is that wouldn't get you first. What about the ultra-high vacuum? Well, it's kind of the same thing with the Marshmallow Man before. Your head, would get got by the vacuum, but people have done studies in outer space of astronauts and how long they could survive in the vacuum of outer space. Now, I don't actually know how the two vacuums compare, but that information says that you could survive in outer space with your spacesuit open for about 10 seconds before you were ripped apart by the vacuum. So I don't think that's going to get you first. So what about heat from the beam? Well, this is a challenge, actually. Heat from the beam is an interesting one because it's actually incredibly difficult to stop the beam. And if you put your head in the way of the Large Hadron Collider beam, unlike what some of these people in the video thought, it would actually go straight through and out the other side. In fact, it has enough energy to go through your head and out the other side about 100,000 times before it loses all its energy. And that's actually one of the issues they had to deal with when designing the machine, is how do you stop the beam? You know, and we want to stop it occasionally, intentionally, because we're done with that particular fill of the beam, or because we think there might be a problem somewhere, so we want to get the beam out and dump it. So they had to put a lot of effort into designing what they call the beam dump, which is a massive long block of very dense graphite, which absorbs the energy. But even then, there's so much energy that they can't just dump it directly on it, or the thermal shock would make the thing explode. So they actually have to paint the beam in sort of a swirly pattern in order to spread out the load of the heat from the beam on this huge graphite block. If you just put this beam onto a massive block of copper, you could actually melt 600 tons of copper from solid to liquid just using the Large Hadron Collider beam. So it's interesting, even though it seems like a stupid question to say what would happen if you stuck your head in it, it does actually present some interesting real problems in engineering in actually designing these machines. Radiation effects. Quite a few of you were keen on this one. Yeah, it's happened. So there's this guy, Anatoly Vygotsky, who once, before the days of such strict health and safety, somehow managed to bypass a safety mechanism on an accelerator and stick his head in a 76 GeV proton beam. Now that's quite a lot lower in energy than the Large Hadron Collider beam. But the amazing thing is that he just saw a really bright flash and he didn't feel any pain at all, which is interesting. Most people think, well, this beam, it's got lots of energy, it will just destroy you. But actually, that's not quite what happened. And after it happened, his face swelled right up, and the skin on that side peeled off, but he didn't die. And in fact, at the time, he was studying for his PhD, and he went on to get his PhD, and his didn't put him off. He worked as a scientist for many years, and he's actually still alive in Russia, living in relative obscurity. I'd love to know really what he's up to now. A journalist interviewed him a few years ago and went to see him, and because the side of his face that the beam irradiated was paralyzed because of the dose of radiation, and he hasn't been able to move the skin on that side of his face for so many years, that side of his face looks like it was pretty much the day that this accident occurred. When I first read this, I was like, miracle cure for aging. Yeah, paralyzed face is probably not a miracle cure for aging, but there you go. So he looks like he did 19 years ago on one side of his face. So you can actually put your head in the beam of an accelerator and survive it. And he's not the only one to have done it. In the days of Cockcroft and Walton, when they were first developing particle accelerators, they didn't know about the dangers of radiation. And so one of the ways that they countered the events or what was happening in some of their nuclear physics experiments was actually to sit under the thing, under the beam. The beam would come down, some nuclear reaction would happen, and then they'd have this fluorescent screen that would light up every time what they were looking for happened. And they would sit there and count each time it lit up, sitting underneath the beam, being irradiated. Now, actually, these people, lived relatively healthy lives, and Cockcroft and Walton got a Nobel Prize for their work, which doesn't justify it, but there have been people who have stuck their heads in particle accelerators. Nowadays, you wouldn't want to do that voluntarily, and you wouldn't want to do it without understanding the consequences. But there are some situations that you might want to do it in, and there's a very good reason for that. Because if you take a much lower energy beam than the Large Hadron Collider beam, and you put it into water or to the human body or into tissue, and you start it with the correct amount of energy, it will actually slow down and stop and deposit almost all of its dose or its energy in one spot. And we call this the Bragg peak. Now, the radiation dose that the LHC beam could give you could kill you 76,000 times over. But the radiation dose you'd receive from a beam of, say, 200 MeV, a relatively modest proton beam, is much lower and can actually be used to treat cancer. And we use this in something called proton therapy, which we're getting in the UK. We did actually pioneer it, and then it hasn't quite come back onto the NHS yet. But in cancer therapy, usually you like to direct a dose of radiation exactly where you'd like it. So in this case, This is a child with their spine that needs irradiating. They've had a tumour removed from the base of the skull, and they need to irradiate the spine in order to stop the cancer spreading down the spine to save that child later in life. Now, with X-rays, with usual X-ray radiotherapy, the dose distribution there is the best that we can do, using all modern techniques. You can see that underneath the spine, in the sort of stomach area, there is quite a lot of radiation dose that we might not want to be there. If you use protons instead, you can actually get a much better defined distribution of the dose. And this is really a fantastic treatment. It is more expensive than X-ray radiotherapy, but based on the basic physics of how a beam reacts inside the body or inside tissue, I think it's a fantastic treatment and one that we should look forward to using in the future. So look it up if there's anything else. So it sounded like a crazy question, but if you had a brain tumour, you might very well want to stick your head in the beam of a particle accelerator. Moving on. Number 3. Don't use a particle accelerator as a death ray. Now, when I was putting together this lecture, I asked the question to my colleagues, my very esteemed colleagues, has anyone ever tried to develop an accelerator as a weapon? And they said, oh, mumble, mumble, Cold War, space, Star Wars, something or other. No, that was their conclusion. They were wrong. People in the US did think about building a particle accelerator, called a neutral beam accelerator, that they would launch into space. That's the first bit, which is a bit wacky. And then they would use it to shoot down satellites and shoot down missiles and destroy anything that they didn't like because they were going to have this super powerful beam in space. Well, they quickly realized that this was crazy and that they were never going to be able to actually make a weapon out of one of these machines, mostly for the reasons that I explained before. Even if you had the Large Hadron Collider in space, I have no idea how you get it up there, but even if you did, it would actually be difficult to do damage with it, mostly because the beam would just go through things and out the other side. But they did, in fact, one of the interesting things I discovered, they did put a particle accelerator in space, which I think is fantastic. They developed this machine, which was only about this big, and they used ultra-lightweight materials, and it only weighed about 50 kilograms. So compare that with a 27-kilometre-long ring. 50 kilograms. It was only low energy, but they just built it. They sent it up in a rocket, and they actually tested it in space, and then they brought it back down to Earth, and they tested it again on the Earth, and it still worked, which I think is an incredible feat of engineering. And people really haven't heard of this experiment before, so I thought I'd point you towards it if you're interested. It's called the Bear Project in 1989. And I have a contact who worked on it if you really want to find out more. So we can't use them as a weapon. Oh yeah, sorry, no deployed weapon has ever used this technology. Okay, what could you do though if you took particle accelerators and you made them really powerful? And this is something that I work on, is taking proton accelerators of relatively low energy, but putting more and more particles in and getting a really high beam power. And one of the reasons we want to do this is because we want to drive something called an accelerator-driven subcritical reactor. This is where you take a nuclear reactor, a fission reactor. In the core, instead of having uranium, it has an element called thorium, which is actually much more abundant, and you don't have to refine it, you can use all of it. Hook up to the reactor a particle accelerator, a very high-power proton accelerator. So the protons come in, and they smash into a heavy metal target and create neutrons. And it's those neutrons then that drive the reaction in the reactor. So without the accelerator there, the reactor is subcritical. It doesn't produce energy. It doesn't sustain a chain reaction. But once you add in the accelerator, you can continue to drive the reaction and generate energy. And in fact, you could transmute existing nuclear waste into something much shorter lived and much safer. So there's some really interesting applications of accelerators way outside of the realm of particle physics that we're starting to get a handle on. The only problem is the accelerator for this is about 10 times more powerful. The requirement is about 10 times more powerful than the ones that we can currently make. So there's lots of challenges for people like me who design accelerators to try and come up with ways of making them more and more powerful for very good reason. So we can't use it as a weapon of mass destruction. this was another one that someone told me, that the thing they shouldn't do with a particle accelerator is you shouldn't eat it, which is true. At a basic level, you shouldn't physically eat the particle accelerator. That's probably a bad idea. There's this guy called Monsieur Mongetou, who was a Frenchman, who, according to Wikipedia, ate all of these crazy things. Even he, though, wouldn't eat a particle accelerator because parts of the machine become radioactive, and while he seems to be fairly stupid, given the things he ate, even he wouldn't go that far. Now, I just want to give you a very quick... there's an aeroplane there, and 400 meters of chain. So let me just give you a very quick reminder of radiation. So what is radiation? It's energy in the form of moving particles or waves emitted by an atom or another body as it changes from one energy state to another. That's the official definition. And you can have two sort of main types of radiation, which are ionizing or non-ionizing. Now, ionizing radiation is the stuff that does us damage. And there's three sort of types which you're probably familiar with, called alpha, beta, and gamma radiation. Just to remind you of alpha radiation won't go through your hand, beta radiation will go through a piece of aluminium, and gamma radiation is penetrating and won't go through a big piece of lead. So there you go, you've been reminded of what radiation is. So can you put your hand up for me if you think that radiation is scary? I'm going to put my hand up. If it's a thing to be afraid of. Less people than I thought. Okay. Not so scared of radiation. Okay. Can I have a volunteer, please? One of those people who said they were afraid of radiation. Could you come down for me? Do you want to come down? And could I have another volunteer who's not afraid of radiation, please? Yep. Do you want to come down? Thank you. So if you would like to stand on this side, and you can hold this thing with the radioactive symbol on it. There you are. Don't lick it. You can hold some bananas, okay? Can you stand to the right over there? Thank you. Okay. Is the thing that you're holding radioactive? What do you think?
Yeah, it probably is.
Yeah, it probably is. Radioactive bananas.
I'm guessing it is.
You're guessing it is? Since it has a radiation, yeah, that one's pretty easy. Okay, so the interesting thing about radiation is it is naturally present in most of the things around us, and this is why he's now slightly afraid of the bananas over there. How many bananas do you think you'd have to eat to get a dose of radiation that would make you sick, even?
You'd probably get sick after about 50.
Well, just from eating them, you get sick after eating about 50.
Yeah.
Okay, but they are actually radioactive. You might not have known. Yeah, it's potassium in the bananas. It contains potassium. A very small percentage of potassium is naturally radioactive. But you'd actually have to eat 5 million bananas in one sitting to get sick. So as you said, you'd probably get sick from eating about 50 of them just physically from eating them before the bananas posed any threat to your health. That thing that you're holding there is radioactive. They're called thoriated rods, and they're used in welding. You can actually just buy them. This thing I'm holding here is called a Geiger counter, and it will tell us whether or not these things are radioactive. So just to show you, can you hear that? Mm-hmm. Yeah. Okay. So there is something coming off there, just to demonstrate that the bananas are really only very mildly radioactive. We can't pick them up with a Geiger counter. It really is very mild. So when we're thinking about radiation and radioactivity, it is worth keeping in mind that just the fact that something is radioactive does not mean it's harmful to us at all. Can you put those down? And can you thank my two volunteers? Thank you very much. This is a naturally radioactive food, and there are foods which are naturally radioactive. But most of us would like to think we've never eaten food that's actually been in a particle accelerator, right? That sounds a bit crazy. So surely we don't eat anything that's been in a particle accelerator. Well, in the UK, we don't eat many things that have been in a particle accelerator, but things like herbs and spices and some other things occasionally go through a process called cold pasteurization or electronic pasteurization, which uses electrons from a particle accelerator to treat the food. Now, it is legal legal, not illegal, in the UK and in the EU. And it's fully authorised, and there's a number of foods that you can find which have been irradiated or could have been irradiated, and that goes all the way through from bananas. So sometimes they're treated with this process to slow down the ripening process, so that they can stay greener for longer, so they have a longer shelf life. And as you increase the amount of radiation that these things are treated with, you go from some grains, seafood, to kill bacteria. Herbs and spices are a more common one, and then even sometimes higher doses on things like poultry to kill salmonella. Now, I tried to go in the supermarket and find things which said that they'd been irradiated, because according to EU law, it has to be labelled on the packaging to say that it's been irradiated. And I couldn't find anything that had been irradiated in a UK supermarket. So I think in the UK, we don't get much of this. Even these things that I'm holding, actually, this is not a brand advertisement. Even herbs and spices, I couldn't find any that have been irradiated. But it's quite common if you travel or if you go to other parts of Europe or the US to find things which have been irradiated. And in the US, if you see this green symbol on your food, that doesn't mean it's organic, it means it's been irradiated. Which is a little bit misleading if you ask me, but never mind. But one of the things I want to point out to you is that this is not a dangerous process. In fact, it's a really, really useful process to kill the bacteria in our food and make it healthy for human consumption. And just because we've irradiated it does not mean that it becomes radioactive. So there's a distinct difference here between a naturally radioactive food or something that's actually, could genuinely be harmful to me if I ate it, and food which has been irradiated, because it's only gone through that process to treat it, to make it fit for human consumption. And there's one place that I can think of that, maybe you might get to go eventually, that you really, really wouldn't want bacteria or you wouldn't want food poisoning, and that you would probably elect to say, yes, if I'm going there, I want my food irradiated before I go. The worst place I could think of to get food poisoning is when you're in one of those. And a lot of astronauts' food is irradiated before they send it up, so that they really, really aren't going to get sick from it. So, yes, you probably have eaten something that's been through a particle accelerator, but perhaps you're more or less concerned about that than you are about eating horse meat. I don't know. So the final thing I think you probably shouldn't do with a particle accelerator is you probably shouldn't destroy the Earth with it. Now, I don't know why I need to say this even, but people seem to think that when we design new massive particle accelerators that are going to have particles that are at huge energies that we've never created before in the lab, that somehow that we just built it for the lulz and that we're going to destroy the Earth with it, and that we haven't quite thought it through, and that we're not quite sure what we're doing. And yes. If you're at all concerned, please go to Has the Large Hadron Collider Destroyed the World Yet.com, and well, you can tell me what you find there. But in answer to some of the questions that we had a few years ago when the Large Hadron Collider started up, of, could it destroy the world? The answer, and the most convincing answer to me as to why it couldn't, is because we have particles in outer space from cosmic rays and things like that at much, much higher energies than we could ever dream of creating in the lab. And so far, they haven't done anything catastrophic to us, and we're perfectly fine. So in terms of just reaching a higher and higher energy, I think it doesn't really matter what we do in the lab, that we should be safe on Earth from these high energy particles. And if we start creating things like mini black holes, which we may or may not, they will pop out of existence so quickly that they wouldn't have time to suck any matter in. And the interesting message that I take from this is that these machines are built so infrequently, 25, 30 years between these big accelerators. Every time it happens, I'm told by my sort of retired colleagues, this happens every time, this scare story that we're going to destroy the Earth with it. Because it's so long between them that people actually forget the media hype that happened last time around. So I'm tasking you with the job. When you're older, if one of these machines starts up and people start going, oh, it's going to destroy the Earth, that you think, I've heard this before. It's not really going to happen. So I'd just like to finish by saying that sometimes some of our craziest ideas, and I've been through some pretty crazy ideas of things that you could do with a particle accelerator here. But sometimes they turn out to be surprisingly good ones if you do them in the right way. And these machines are not just useful for particle physics, they're useful for all sorts of other things, like cancer treatment, like killing bacteria in food, and other things I haven't discussed, like carbon dating and imaging down to the atomic scale and all sorts of other things. And I'd just like to leave you with my advice in choosing your career for what it's worth. And that is to find something that makes you sit up and think, this is really important, or this is fascinating, or this is what I'm passionate about. And it can be in any area, really. It can be something like space might get you, or climate change might be a concern. You might really love astronomy, or you might be more passionate about world hunger, injustices in the world, the availability of water, energy, health, aging, anything like that. Think about it and do something about it. That's all really you need to do. And make a career out of doing something about it. Because if you do something that you're passionate about and you really, you love, you're not going to even feel like you're going to work each day. You're just going to feel like you're getting up and you're doing what it is that you're passionate about. And while you do that, don't be afraid to challenge yourself. Don't shy off doing something just because you think it's hard. It's when we do something hard that we really make a difference. So dig deep and don't be afraid to dream. And I will leave you with some photographs of some of the places that my career in physics has taken me so far, and I hope to add many more to this list in the future. So that's 5 things you should never do with a particle accelerator. Thank you.